I have to say that what we're going to do today is not, at least the first thing we're going to do today is not all that interesting. Okay, so it's sort of a specialized trick. Okay, on how to do integrals that have trigonometric integrands. Okay, so the first thing is some what you call trigonometric integrals. Okay, so like I said, these aren't the most interesting thing, and it's basically a bunch of small tricks. Okay, just a collection of tricks to deal with these. I don't think these are that important. I'm going to show you some of the tricks. I'm not going to show you all of the tricks. Okay, so we're going to do basically a bunch of examples. Okay, so trigonometric integrals. Somebody gives you this cosine, the integral of cosine cubed. Okay, and says integrate this. Okay. Well, it's not so easy to do just by looking at it. But one thing you could do is to use the trigonometric identity. Right? You know that cosine squared plus sine squared equals 1. Right? You know that cosine squared plus sine squared equals 1. And so you can replace the cosine squared by 1 minus sine squared. Right? So you say, okay, this is 1 minus sine squared. Right? And then you have a cosine left over. Okay, right? And that's good. That's good because then you've got the integral of cosine, and you've got this minus sine squared cosine. Right? And those things are easy to integrate. Like, what's the integral of cosine? What's the antiderivative of cosine? Sine, right? Sine. And what's the antiderivative of sine squared x cosine x, or negative sine squared x cosine x? Should I let you think about it? Take half a minute, take 30 seconds, and figure this one out. Right? You've got this sine squared x cosine x dx. Yeah, take half a minute to do that. I forgot your name. What's your name? All right. Okay, that should be enough time to do it, I think. So turn to somebody next to you and say, this was the answer. So what's the answer? Who can give it to me? Bumpy. How about you? 1 over 6 times, oh yeah, 1 over 6 times sine x, let's see. So how did you do it? No, right, so let's take a look here. Right, so you did some sort of u substitution, right? What did you take as your u? U is sine x, right? Du is cosine x dx, right? So here you switch this over, you get u squared du, right? And then when you integrate that, what do you get? What's the integral of u squared? Well, it'll be u cubed over 3, right? So u cubed over 3 plus c. And so you end up with sine cubed over 3. Did you do something different? Do you want to tell me what you did, and I can. You found where you went wrong? Yeah. Okay. Okay. Right. Everyone okay with that? With this thing? Okay. So you end up with sine x minus sine cubed x over 3 plus a constant. Okay. Right. And suppose I had something like cosine to the 5th power, right? Suppose I had cosine to the 5th power. What would happen in that case? What would you do in that case if you had cosine to the 5th power? Who is talking? I know, just one boy. Is it you?
Yeah.
Okay.
You can say it again.
Oh yes, sure. Sorry, I couldn't tell which one of you is. Yeah, okay. The question is, what if the question is this: cosine to the 5th? What if you had something like this? Just now we did cosine cubed. What if you had cosine to the 5th? Does anyone see how we could do basically the same thing? Right. You just do the same thing. Yeah. Chen Xiangyu.
You just times 1 minus sine squared. Times the same 1 minus sine squared.
Yeah, so this, what you could do is you say, well, I'm going to break this. Basically what we did was break it into cosine squared times cosine. Right? We broke the cosine cubed into cosine squared times cosine, and then we replaced the cosine squared using the trigonometric identity. Right? Well, if you have cosine to any odd power, you can basically play the same trick. Right? You can say, well, I'm going to break this into cosine to the 4th times cosine dx, right? And then I'm going to change this into 1 minus sine squared, right? And then you'd go on from there, right? You see that this trick, can be extended. You can use this trick in other similar cases, similar situations. Okay. Any questions about that? Okay. Right, and you can sort of, okay, so here's a very similar one. Here's a similar one. Sine to the 5th x cosine squared x dx. Sine to the 5th x cosine squared x dx. Right? How would you break this one up using basically the same trick? Hey, Xiao, go ahead. You cannot see it. Oh, okay, yeah. I'll just stand right here. turn to somebody nearby and say what you're doing. Okay. Who would like to say what we should do? What should we do? You're gonna change the cosine to 1 minus sine squared. Okay. 1 minus sine squared. Okay. And then what would you do with that? You've got the sine to the fifth. Right, you've got the sine to the fifth. So you're going to get sine to the fifth and minus sine to the seventh. Yeah, what do you do with that? What do you do with that afterwards? I'm kind of curious. I mean, there probably is a way to. So you've got sine to the fifth minus sine to the seventh. And then are you gonna try a u substitution? What's your u gonna be? Okay. So you try u is sine x. Your du then is going to be cosine x dx, right? Yeah, right. So it's trouble, right? There's trouble because you don't have the cosine there. Right, you don't have the cosine there. So, maybe going that. Maybe you can do it some other way, but maybe you can still do it. But we're gonna do something similar to the previous trick, which is let's break this up into sine 4x. Sine x. Okay. So we'll break it up into an even power and this one leftover. Okay. Right. And you see what I'm going to do, right? What am I going to do next? I'm going to say 1 minus cosine squared, quantity squared. And then I've got the my u substitution. Cosine will be my u, and I have the some multiple of the derivative here. Okay. Right, so you say, okay, this is going to be 1 minus cosine squared x squared cosine squared, and then something. Right, and so you take your u to be cosine. Oops, yes, you take your u to be cosine. Du is going to be negative sine. Right? And then you go on from there. I'm not going to do it. It's not interesting. Okay. Any questions? Mancini, do you have a question? No? You look like you have a question. You don't have a question. Okay, that's all right. Okay. So maybe I should let you try one more. So try this one by yourselves. Sine to the seventh theta, cosine to the fifth theta d theta. Okay. And I'm just curious how you would break it up. How are you going to break it up? Take half a minute and tell me how you're going to split it so that things work out in the end. Would anybody like to say how they split the integrand? Hoàng Anh Tuấn. Oh, I'm just curious how you split it up at the beginning. What's the first thing you did? Say. Okay, I'll call on somebody else. Yeah. Okay. How about Pan Xini? Pan no. Okay. Anybody like to say? Trong Gong Zi.
I put the cosine 2/5 to the minus sine squared.
Okay.
First squared.
Okay, so you broke this, you said, okay, I'm going to take this as cosine times 1 minus sine squared.
Yeah.
Right? Yeah, that would do it, right? Because then you have sine to the 7th, you've got all these powers of sine, and they're all multiplied by cosine, which is good.
They can work either way.
That's right, this one will work either way. So you could do it, you could break it up. You could take this one and take 4 powers of the cosine, right, and switch those guys over, or you could take 6 powers of the sine and switch those guys over, right? You could also, either way, you could break this up into sine 6 theta times sine, and then make the 6 theta turn into 1 minus cosine squared, right? That'll certainly, either way, you're gonna get the answer. Everyone okay? Anyone have questions about this? Yes? It's not. It's cubed. Thank you. Anybody have questions? Okay. So that's that sort of thing. There's another trick that's pretty common. So another trick. Here's another trick. And this trick, you see, it happens occasionally, so it's kind of useful. Basically, it's using half-angle formulas. Okay, so from trigonometry, if you remember your trigonometry, and I usually don't, but there's these things called half-angle formulas, which tell you that sine squared can be expressed as 1/2 of 1 minus cosine x, and cosine squared can be expressed as 1/2 of 1 plus cosine 2x. Okay, so for example, if you see something like the integral of sine squared, right? Somebody says, what's the integral of sine squared? Well, that's kind of hard to do. If you switch it over to cosine, you have 1 minus cosine squared, right? Doesn't really help you, right? But you can use this half-angle formula and say, okay, this is just 1/2 of 1 minus cosine 2x dx. Right, and that's easy, right? Because you get 1/2 of x plus 1/2 sine, x minus 1/2 sine 2x plus c. So this is another sort of typical trick. If you just have a sine squared, or if you just have a cosine squared, right? Or if you have some even, so right, the stuff we did over here was good for odd powers. Right? You have odd powers. If you have even powers, then often you end up using this sort of trick. So again, like I said, I don't consider these tricks to be all that important. You know, in this day and age, you just put it into a computer and it'll integrate it for you. But I'm just gonna touch on these tricks. Okay. There's one last integral that is kind of that will turn up occasionally. And that's the integral of the secant. Does anyone know how to integrate the secant? This is a funny one. Go ahead, Bob. You look like you know. Or you look like. No, you don't know. That's okay. Does anyone know the trick to this one? This is kind of a funny one. You multiply it by 1. You multiply by 1, but a very funny looking 1. So you take the secant, and then you multiply by 1. Okay, so what you end up with is the integral of secant squared x plus secant tangent over the tangent plus the secant. Right. Secant squared plus secant times tangent over tangent plus secant. Okay. But maybe you recognize what happens, right? You see the relation between the top and the bottom. The top is the top and the bottom are related. Does anyone happen to see the relation? Go ahead. Right, yes. So what you end up with, you see that the top is the derivative of the bottom. Right. So you could write this as this is the integral of du over u, where u is tan plus secant. Right, and so you end up with the natural log of tan plus secant of the absolute value. Okay, are there any questions about these things? Again, it's sort of, these are very particular tricks, right? They're only going to work in this one situation. So it's only if you're interested in integrating trigonometric integrals. Okay, and I think it's not something that happens to most people. Unless, it could happen. Okay, so let's go on to something a bit more interesting, which is called trigonometric substitutions. Trigonometric substitutions. Okay, this is better. Okay. So let's recall. Right, you have the unit circle. You have the unit circle, right, and you have some angle theta, right. Then this point has coordinates cosine theta, sine theta, right. That's what cosine and sine mean, right. They're the coordinates of a point on the unit circle. Okay, and so of course that because they're on the unit circle, you know that cosine squared plus sine squared equals 1. Right? And you also know dividing both sides by cosine squared you get that 1 plus tangent squared equals secant squared. Okay. So, okay. So this leads to our next, this observation, this very simple observation leads to the above. So the above leads to the next trick. Dealing with terms that look like x squared plus or minus a squared. Okay. So plus or minus x squared plus or minus a squared, where x is the variable and a is some constant. Okay, so we'll start off with an example. So start off with an example. Dx over the square root of 1 minus x squared. Okay, so what we're going to do is the following. We'll say, let x be sine theta, where theta ranges between negative pi over 2 and pi over 2. Okay. So again, we're going to do basically a substitution, right? The substitution is theta is sine inverse x, right? This is actually your u substitution, right? U is sine inverse of x. Okay, and that's why we restrict the u to be between negative pi over 2 and pi over 2. Right, because that's what you do for the inverse sine function. Okay, so then dx is going to be cosine theta d theta, right? And we can rewrite this thing. Dx is cosine theta d theta, cosine theta d theta. And then below we end up with 1 minus x squared. Well, that's 1 minus sine squared. Right. Substitution. Right. Really what we're doing is a substitution. We usually write it like this, let x be sine theta, but really the substitution is this. Okay, so then what happens here? The square root of 1 minus sine squared. Well, 1 minus sine squared is cosine squared, so we get the square root of cosine squared, which is going to be the absolute value of the cosine, right? So we get cosine over absolute value of cosine d theta. Fortunately, theta ranges from negative pi over 2 to pi over 2, right? So what can we say about the cosine? The cosine is positive, right? It's positive, so we can get rid of the absolute values, and we get 1 here. Okay, so we get when we integrate 1, we get theta plus c, right? That's to say sine inverse of x plus c. Okay. Which you maybe knew already. We had mentioned, we had just used, in fact we used this formula just yesterday. But if you didn't know it, then we've just derived the formula now. Okay, so maybe you're starting to see what we're going to do with these formulas, right? Whenever you have whenever you have some number minus x squared, well, you're going to take your x to be something like the sine, right? Or maybe the cosine. You know, whenever you have the square root of 1 plus x squared, well, you take your x to be the tangent, right? Et cetera, et cetera. So let me write things down. Okay, so is the system, I guess. If you see x squared, if you see a squared minus x squared, then take x as a sine theta, where again theta ranges between negative pi over 2 and pi over 2. Right? So if I had seen, 4 minus x squared here, then I would have taken x to be 2 sine theta. Right? Whenever you see, say, x squared plus a squared, x squared plus a squared, then what am I going to do? What should I do? You can tell me? Yeah, use the tangent. Right? So you say let x be a tangent theta. Right? And again, you need to do some restriction on where theta is, so that you can talk about because really what you're using is the inverse tangent function. So theta has to be between negative pi over 2 and pi over 2. And the last one, whenever you see x squared minus a squared, then you take x to be a times the secant. With theta in the appropriate place. 0, pi over 2, if x over a is greater than or equal to 1, and pi over 2 times pi, if x over a is less than or equal to negative 1. So let me put up one for you to do. This. So I'd like you to try one as an exercise. X squared plus 1 squared. Okay, so take maybe 2 minutes and give it a try.